Good morning, guys. Hopefully you had a good spring break. It's probably weird again this year, but hopefully you got a chance to relax a bit and catch up on your sleep. In case you haven't checked, I've posted the solutions to the midterm online. And by now, you can also check your own grades. Just to give you an idea of the overall distribution, the top score was 92 and the lowest was a 9. I think the median was 59 and the average was 57. So based on just the midterm alone, I'd expect the AB cutoff to be around in the low 60s and the BC cutoff to be around maybe in the 30s. And I try very hard in this class not to flunk people, or I may give 1 or 2 Ds if people mess up both the midterm and the finals. And don't turn in homework and things like that. In case you haven't done well in the midterms, there's absolutely no need to panic at all, because first of all, the finals count for more. But even beyond that, what I tend to do is, if I see a person hasn't done well in the midterms, but has done extremely well in the finals, but then when I do the weighted scoring and then I curve things, maybe he or she is on the wrong side of an AB cutoff, but the person's done very well in the finals, I'll bump that person up to an A. Similarly, if you're on the wrong side of the BC cutoff, I'll bump you up to a B if you do very well in the finals. So the message is, if you've done well in the midterms, congratulations. But if you haven't, no need to despair. You can recover, plenty of time to recover during the final exam. Okay. So take a look at the solution, and if you have any questions with the grading, shoot me an email, and then we'll respond to you. Okay. All right, so let's move on. Normally, I would have gone over the midterm solutions, but since we have lost 3 lectures, we are behind schedule, so I'm going to just push ahead. Okay. So before the midterms, in chapter 3, we looked at the mechanism for moving carriers, electrons and holes, by what is known as electron drift. And we said that if you have an electric field, say pointing to the right, holes which are positively charged will see a force in the direction of the electric field, and they'll move with an average velocity, which is called the drift velocity, proportional to the electric field. And the proportionality constant is the mobility of the carrier. So it'll be mu p times electric field will be the average drift velocity. They'll then give rise to a drift current for a single hole. But then, of course, if you have p holes per unit volume, to get the total number of particles flowing per unit area per second, you multiply by p mu times electric field. That gives you the flow of particles. To get the corresponding current, you multiply by the charge of a hole, which is plus q. That gives you the current density. And then to get the total current, you multiply by the cross-sectional area of the device. Now, the expression, if you think about it, is a little bit strange, because what it tells you is that the velocity is proportional to the electric field. Okay. Now, normally, based on Newton's equations, we know that dp dt, the time rate of change of momentum, equals force, which in this case would be q times electric field. So with a constant electric field, according to Newton's second law, you'd have expected a constant acceleration, not a constant velocity. Okay. And the reason we end up getting a constant steady state velocity is because of the frictional forces in the solid, what we call scattering or collisions. Okay. So although the electric field tends to accelerate the particles, the collisions with the defects in the crystal constantly slow them down, and you reach a steady state. The analogy would be, if you drop an object from high up in the atmosphere, it'll accelerate due to gravity, but then it undergoes, as it picks up more and more speed, it has more and more friction with the atmosphere, and at some point, it'll reach a steady state velocity. Don't keep accelerating because of the frictional forces of the atmosphere. So same kind of thing happens over here. Then in chapter 4, before the midterms, we started talking about what are called excess carriers under non-equilibrium. What does non-equilibrium mean? Well, if I take a semiconductor device, such as a transistor, and it's just sitting on the table, very lazy, no voltage is hooked up to it, no laser light shining on it, it's just sitting there. Okay. But even though it's just sitting there and it's under so-called equilibrium, it's a funny kind of an equilibrium. It's called dynamic equilibrium, not a static equilibrium. So it's not as if anything's not happening at all. It's just that there's no net motion of carriers and things like that, okay? What is always going to happen, and that you cannot turn off, is this phenomena of black body radiation that constantly surrounds us. And these black body photons are constantly going to be absorbed by the semiconductor, exciting electron hole pairs. Then after a few picoseconds or nanoseconds, those electrons will fall into the empty hole states and re-emit the black body photons. So there's a constant exchange of photons with the environment. And that's what establishes N sub I, the intrinsic carrier concentration, which of course would be a function of temperature, because higher the temperature, more black body photons in the environment. Then if you apply, say, a DC voltage, you start getting this drift current that you talk about. So that's an example of non-equilibrium. But if it's just a DC voltage, there would be a steady state non-equilibrium. And then finally, if you apply an AC voltage, currents would change as a function of time. So that would be a transient non-equilibrium scenario. Okay, so I want you to have these concepts clear in your mind. Okay. Now, under certain conditions, when you apply voltages or you shine a light non-uniformly on a semiconductor, you may create more electrons or holes in one region and have fewer electrons and holes in another region. That then gives rise to the second mechanism for carrier motion, which is called diffusion. Okay, and this is where we left off before the midterms. To understand this physics of diffusion, you have to realize that the electrons and holes in a semiconductor, even in the absence of electric fields applied to it, are not going to be static. They're constantly bouncing around, as shown in this cartoon view over here. Okay, and this constant motion in random directions is known as Brownian motion. Brownian motion. Okay, this was discovered in the 19th century by an English botanist, Robert Brown, who looked at a glass of water under a microscope, and he looked at these tiny dust particles in the water, not static, but constantly bouncing back and forth randomly. It wouldn't slow down. And of course, he had no idea what the heck was going on. Neither did anybody else. And it took Albert Einstein in 1905 to look at that physics and realize that was experimental evidence of atoms. Okay, and he said that atoms are molecules. And he said that the way you can understand this Brownian motion, this random erratic motion, is you have these tiny dust particles which are being bombarded by these molecules of water in all kinds of directions because of this random motion of these molecules. And because there's a statistical difference of the number of hits, say from the left versus right, there'll be a net force, a random force, and that's what causes these dust particles or pollen particles to jiggle around, okay? So the same kind of physics is shown over here, but of course, not for pollen particles in water, but electrons or holes moving in a semiconductor. So the way to visualize this, if you look at a particular particle, say a hole, it moves in a straight line from here to there, say. It's not bumping into the periodic arrangement of atoms, because remember, that does not cause any collisions or scattering, but at some point it does undergo scattering. Who can tell me what that scattering is due to?
Imperfections or
Very
defects
good.
in the lattice.
Excellent. Excellent. So it's not bumping into a periodic arrangement of the silicon atoms. It's some kind of a defect. And that could be, say, an extra silicon atom or missing silicon atom, or a foreign impurity that you may have put in purposely, such as a donor or an acceptor. Or it could be even these atoms jiggling around the equilibrium position. And those, of course, are called the lattice vibrational modes or phonons. So anything that is a deviation from perfect periodicity is what causes this scattering, not the periodic arrangement of the atoms themselves, which Drudy, the physicist Drudy, initially thought. Okay, so quantum mechanics came later on, and they realized that the scattering is not caused by the periodic arrangement of the atoms. That merely changes the true electron or hole mass into an effective mass. The scattering is caused by imperfections. All right, anyway, it bumps into an imperfection, travels in a straight line across hundreds of this periodic arrangement of atoms, bumps into another imperfection, and so on and so forth, okay? So what you'd find is, in the absence of electric fields, even though it's jiggling around very, very rapidly, it doesn't go very far, okay? And not only that, of course, you have not just one hole, say, you have an Avogadro number of holes, the other hole might be doing this. The net result is, if I look at any cross section, there'll be as many holes moving to the right as moving to the left, and there'll be a net cancellation of the current, and there's no net current, which is what you'd expect in the absence of an electric field, okay? Now, this random velocity is called the random thermal velocity, and is given by the average distance between these collisions, which is called the mean free path L, divided by tau, which is the mean time between collisions. Okay, so average distance divided by average time gives you the average velocity. Now, there's a theorem in physics, in thermodynamics, which is known as the equipartition theorem, that I'm just going to equipartition theorem, which states that when particles move around, any particle, not just electrons or holes, they have an average kinetic energy per degree of freedom. What does the degree of freedom mean? That means movement along the x-axis, y-axis, or z-axis. Okay, so per degree of freedom, the average kinetic energy, half mv thermal squared, is given by kT over 2. Now, the quantity kT is known as the thermal energy of the system. K is the Boltzmann constant, T is temperature, room temperature is 300 Kelvin. At room temperature, that happens to be 0.026 electron volts, or approximately 26 MeV, or sometimes we'll approximate that as 25 MeV. Okay, so that's approximately equal to 1/40 electron volts in round numbers. All right, so that's if it's a one-dimensional motion. In 3D, you get half kT in each dimension, and you get 3/2 kT. Okay, now we just do a rough ballpark estimate in many cases, and we'll say that the average kinetic energy is of the order of magnitude of kT. Now, clearly, you see then that if the system is heated up, T is higher, this jiggling around will be more violent, as you might expect. All right. All right. Now, so far, of course, we are looking at a uniform system, and you have this Avogadro number of particles which are jiggling around, rapid Brownian motion. There's no net motion from one end to the other. Now let's look at non-uniform distributions of particles. Non-uniform distributions. Okay, and look at one particular example of a delta function distribution of carriers, say of electrons. So I have this high concentration of electrons shown by this blue rectangle at location x equal to 0, okay? And then I let the system go, and they're going to jiggle around, okay? And you can find out when you do the solution that after time t1, these particles, some will diffuse to the left. This motion of particles from a high concentration region to low concentration region by this random Brownian motion is a process known as diffusion. Then some particles will diffuse to the right and will spread out, and one can prove that the shape of that curve will be a Gaussian curve. Okay. If you wait longer, the thing spreads out more and more. Okay. And we'll prove later on that the spread of this Gaussian is proportional to the square root of time. Okay. Now, the physics of this is the same kind of physics as this following analogy. Okay. So if we are meeting in the classroom, okay, I'd bring along with me a bottle of perfume. And if I had opened the bottle of perfume, after a while, the folks in the first row would have been able to smell the perfume, because these perfume molecules would have high concentration right above the open bottle, and they jiggle around because of random Brownian motion in air, and it would diffuse the first row. If you waited a little bit longer, the folks in the second row would start smelling it. Okay? And then if you waited a very, very long time, all the perfume would have evaporated. And in this whole classroom, you'd have a uniform distribution of these perfume molecules per unit volume. And at that point, there would be no net diffusion, okay? Because diffusion is driven by concentration gradients. Okay. Now, using the same analogy, what would be the drift mechanism that we discussed in chapter 3? The drift mechanism would be if behind this perfume molecule I had a fan blowing. Okay, so the fan would be like a drift current, if you will, driving the perfume molecules. But if I didn't have the fan blowing, the motion due to the concentration gradients would be diffusion. All right. So let's try to come up with a formula for this diffusion current. Okay. The way you do that is you look at a distribution n of x, which is shown by this blue line. Okay. And I'll prove that there'll be a diffusion of electrons from the left to the right, from the high to the low concentration region. And the flow will be proportional to the concentration gradient, dN dx, or dP dx in the case of holes. Okay. The way you prove that expression is you break down this distribution into a series of these histograms as shown over here. Okay. Each of length L, this mean free paths that I showed on the previous slide. Okay. Just rough order of magnitude. Okay. Now, this histogram is slightly higher than this histogram. Okay. Then for each of these histograms, we saw that it spreads out in the form of a Gaussian. This will spread out in the form of a Gaussian. Okay. And what I want to find out is what is the net flux phi of electrons to the right in this case. Okay. And what are the units of flux? Units of flux are number of particles flowing across unit area, say centimeter square per second. Okay. So the units of flux are number of particles flowing across a cross section, say at this point, per unit area per second. Okay. So if I zoom in on this particular cross section between these two histograms, okay, at location x0, so I'm now blowing it up over here. So I am interested in the net flow across x0, okay? And each of these, of course, are spreading out in histograms. But since this concentration N2 is lower than N1, one can show that there'll be a net motion of particles to the right, okay? So the particle flow from the left to the right minus right to the left is a net flow of particles, okay? From the left to the right, it's given by half V thermal, concentration of the electrons at x equal to minus L at this location, the average point. And the flow to the left would be the concentration at x equal to plus L flowing to the left. Now notice it has the right units, okay, because the units of concentration are number of particles per unit volume, okay? The dimensions of thermal velocity are centimeter per second. So if I cancel the centimeter with the centimeter cubed, I get number per centimeter square per second. Okay. Next, what I do is I divide by L and do the averaging because the factor of 2 is, of course, because of the averaging. Okay. Next, what I do is I divide by L and then I have to multiply by L as shown over here. That doesn't change anything. Okay. Now, L times V thermal, if I look at this expression over here, if I take L times V thermal, I get V thermal squared on this side, okay? And then N at L minus N at minus L divided by 2L is nothing but the concentration gradient, dN dx. Remember that L is a mean free path, is a pretty small number, so you can kind of almost assume the limit of L going to 0. So approximately it's a slope, and that works out to dN dx. But there's a minus sign because clearly the diffusion happens from the high to the low concentration region. Okay. Everybody with me so far? Now this quantity L times V thermal, I define as a new parameter, which is called the diffusion coefficient or diffusivity, in this case for the electrons. And that has units of centimeter square per second. Why? Where length has, of course, units centimeter, V thermal is centimeter per second. So the dimensions of D, the diffusivity, is centimeter square per second. Okay. You can see this over here also because L times V thermal would be V thermal squared times tau. That also has units of centimeter square per second. Okay. Now the quantity flux simply gives you the particle flow per unit area. To get the actual current due to that, you have to multiply by the charge, which for the case of electrons is minus Q. But remember the diffusion itself had a minus sign, and the two minuses cancel out, and you get a net positive sign. Okay, that gives you the current density per unit area. If I wanted the actual current, IN, you have to multiply that by the cross-sectional area of the device. So you look at the cross-sectional area of the device, A, okay, and the net current will be A times that. So that is the expression for the diffusion current due to electrons. This next slide is very, very important.
Are you getting dn dx from the slope? I'm a bit confused on where you're pulling dn dx from here.
Yeah, the dn dx is from the slope. Yes, exactly. Because
okay, so you just have to know that, or would you have to have another equation to calculate it?
No, you can see this from this, right? Because this expression over here is n evaluated at minus L. So that's this concentration N1, right? Minus n evaluated at L, that's this concentration N2, divided by the distance between them, L, right? So the distance between these, between the midpoints of the histograms is L, right? The concentration difference is N1 minus N2. So that's n evaluated at minus L minus n evaluated at L, divided by the distance between those, okay? And that in the limit of L going to a very small number is dn dx, right?
Okay, so you would have to be given like the separate values of each point.
Sure, yes.
Okay.
So in general, you'll be given this curve, okay? So so what I'm showing is the diffusion current is proportional to the gradient. So at this point, it will be this value. At this point, the diffusion current will be lower. So the diffusion current will be the highest where the slope is the steepest. Okay.
Okay.
All right. So the next slide, as I said, is a very, very important slide. You should study it very carefully for the midterm exam, for the final exams, because this summarizes all the current mechanisms in a semiconductor. And this is a summary of chapter both 3 and chapter 4. Okay. So let's go through this carefully. So let's first start with the diffusion, which is what I'm talking about. So in this particular example, I have both a concentration gradient, say, of electrons and a concentration gradient of holes. And I want to figure out which direction the diffusion would be. Well, diffusion always is from the high concentration region to the low concentration region, right? Because you have a random Brownian motion of these particles, you have a random Brownian motion of these particles, but if I have a higher concentration over here, then over here, there'd be a net flow this way. Similarly for holes, there'd be a net flow of holes, okay? But there's a critical difference, and the difference is for electrons, the charge Q is negative, while for holes, it's positive, okay, obviously. All right, so let's see which way the fluxes of the particles would be, okay? Now, in this particular example, because the concentration gradient is from decreasing from the left to the right, so the flux due to diffusion, both for holes and for electrons, is to the right. The flow is going to be from the left to the right, from the high to the low concentration region, okay? Now, what would be the corresponding directions of the current densities due to diffusion? Well, diffusion of holes with a charge of plus Q would then give rise to a current in the same direction, right? On the other hand, for the electrons are diffusing to the right, but the current due to that points in the opposite direction, right? Because they have a negative charge. In chapter 3, we looked at the drift mechanism. So I'm showing that just for the sake of completeness. So let's assume that the electric field also points to the right. Now, who can tell me which direction the holes would move? Would they move to the right or to the left?
Also to the right.
To the right.
Right, because they have a positive charge, okay? So the flux of holes due to drift is to the right, okay? Now, if the holes drift to the right, which direction is the current, drift current due to the holes? To the right or to the left?
To the right.
Right, because once again, they have a positive
Right,
charge,
yeah.
okay? Right. Now, the electrons are always trickier, okay? So the electric field points to the right. Which way do the electrons drift?
Left.
Left, okay?
Negative
But
charge.
yeah, exactly. Very good. Because it's minus Q times electric field. But if they drift to the left, which way is the current due to that? They have a negative charge.
The electrons drift to the left?
Yeah, electrons drift to the left, right? The particles themselves, because
right still, because current is opposite of the electron movement.
Very good. So the actual current is to the right. So for the electrons, the drift of the electrons is to the left, but the current due to that is to the right. Okay, so look to this. So this is sort of a worked out example, if you will. Okay, and make sure that you get these vectors correct, because I'll probably give you a question on that in the final exam. Okay, now let's write down the expression of the current. So this is sort of the master equation, and the rest of the semester will be an application of this equation. Okay, so what do I have? I get the net current equal to the current densities due to electrons and holes. Current density is amps per centimeter square times the cross-sectional area of the current flow in the device. Okay, so that's A. Okay, now let's write down the expression of the current densities. Due to drift, we saw that assuming the electric fields were low enough, you get a velocity, drift velocity, which is proportional to the electric field, and the proportionality constant is what we call mobility, mu n times electric field. That, of course, gives you the drift current due to a single electron. If I have n electrons per unit volume, the flux will be n times the drift velocity, n mu e. That gives you the flow of particles. You get the actual current, you get multiplied by the charge of the electron. Okay, now you get a net positive sign because the drift velocity is minus times the electric field, but then the charge of the electron is also minus, so the two minuses give you a net plus. Okay, on the other hand, for the holes, I have the electric field to the right. The drift velocity is plus mu times electric field. That gives the current due to a single hole. For a hole density of P, you multiply by the P, also to the right, and then multiply by the charge of the hole, which is positive. So you get a net positive. So you find that the drift currents actually end up pointing in the same direction of the electric field, Jn drift and Jp drift. Okay, they both point to the right in this particular example, in the same direction as the electric field. Now, how about for the diffusion currents? Okay, let's look at the holes. That's a little bit easier because of the positive charge. Which way do you think that the hole diffusion will be? To the right or to the left? Because of this random Brownian motion. So random Brownian motion over here, but the concentration is higher over here. Random Brownian motion, but the concentration is lower over there. Which way do you think the net flow would be due to random Brownian motion? To the right or to the left?
To the right.
To the right. Very good. Okay. And there's going to be a minus sign because it's from the high to the low concentration region, right? So notice that this is a negative slope, but the flow is in the positive x direction, right? So it's minus dp dx, that's a concentration gradient, times the whole diffusivity or the whole diffusion coefficient, which, as I said, has units of centimeters square per second, gives you the whole flux, phi p, due to diffusion. To get the actual current due to that, you should multiply with the charge of the hole, which is plus q. And notice that the minus sign stays put because the whole charge is plus q. That gives you the current density. To get the actual current, you multiply with the cross-sectional area. Okay, so that's my drift current of holes. That's my diffusion current of holes. Okay, the final term is the electron diffusion. Once again, the electrons diffuse from the left to the right because of this concentration gradient. Okay, so that's given by dn dx times dn, which has a minus sign. But then to get the actual current, you multiply with the charge of the electron, which is minus q, and the two minuses cancel and you get a plus. But they don't cancel in the case of holes because the whole charge is plus q. Okay, so this, like I said, is the master equation. So this is electron drift, electron diffusion, hole drift, hole diffusion. Okay, so in general, in any semiconductor device, you'll have four components of current possible. Now let's see what the functional dependencies are. Okay, so for the drift currents, I find that they're proportional to the concentrations themselves, N or P. While for the diffusion currents, they're not proportional to the concentration, they're proportional to the concentration gradients. That's a key difference. Okay, let's do a thought experiment. So if I had two cases, okay, case one, where the concentration is like this, and case two, like this. So that's case 1, case 2, and let's assume these are for holes, okay, just to make our life simple. So they have a positive charge, okay? Who can tell me, so that this is all as a function of x, okay? Who can tell me which case has a higher diffusion current, case 1 or case 2?
Case 2.
Case 2.
Very good. Who can tell me which case has a higher drift current?
Case 1.
Excellent, excellent, okay? So in the limiting case, if I had a constant concentration slope, the diffusion currents would be 0. You'd only have diffusion currents. Sorry, you only have drift currents. On the other hand, if it's a very low concentration but have a steep slope, the drift currents would be pretty small because the concentrations are small, but you could still have a large diffusion current. Okay, so make sure that you understand the two. Okay.
So for
Yes.
dn d over dx and dp over dx in these equations, are they typically going to be the same due to the lines typically being parallel?
That's a very good question. Okay, so no, not always, but generally yes, but not always. That's an excellent question. I was going to discuss that later on, but since you raised it, that's a good point. Okay, they're typically going to be the same because of this process of space charge neutrality that you mentioned. Remember, we said that in a semiconductor, we have positive charges which are fixed due to, say, the donors, negative charges due to the acceptors, okay? But then on top of that, you have holes which can move around that are mobile, electrons which can move around that are mobile, okay? So you have positive charges, which should be the mobile holes plus fixed donor impurity ions, and negative charges would be the mobile electrons and the fixed acceptor ions. But then if I took any lump of semiconductor where the doping concentrations didn't change very, very rapidly with position, you have space charge neutrality. And all that states is the net negative charges, which is electrons plus acceptor ions, must be balanced by the holes plus the donor ions, okay? However, there's a word of caution that space charge neutrality condition is not an universal law. In fact, pretty soon, I guess from next class, when we start talking about devices, the first device we look at is a p-n junction diode, where the hole doping changes rapidly from a high hole doping on the p side to a low hole doping on the n side. Similarly, the donor concentration changes rapidly from the n side to the p side. And we'll find that in this so-called junction of the depletion region, because the doping concentrations are varying rapidly, space charge neutrality breaks down, okay? However, in cases where the doping concentrations don't change rapidly, and you have space charge neutrality, the electron and the hole concentrations will generally track each other, okay? But if they don't, if the space charge neutrality breaks down, and very often in devices, it will break down, then all bets are off. The gradients may be very different. That's a good question, okay? Now, let me ask you a follow-up question. Even if the concentration gradients are the same, does that tell you that the diffusion currents are going to be the same? Even the magnitudes.
I mean, wouldn't they be? Wouldn't they have to have the same slopes if they were parallel with each other?
Yeah, the slopes are parallel. I'm asking about the diffusion
I guess the
current.
charge, the sign might change, but I don't see anything other than that that would.
How about the DN?
Oh yeah, since it's going from negative to positive and the other one's going from positive to negative.
Right, so the direction changes, but the magnitudes also are different because DN and DP in general will be different. Okay?
Okay.
Yeah. One final question for you guys, okay? Let's look at the drift currents that we talked about. Is this the correct expression for the drift current regardless of the electric field?
Wait, like
So the
master equation?
Yeah, in the master equation. So I showed that the drift velocity being mu p times e or mu n times e, right? So what this is predicting is I have a drift velocity versus electric field, which is linear, right? Whose slope is the mobility. Was that true regardless of the electric field? What happens at high electric fields?
You have a
Doesn't it reach a
saturation velocity.
Very good. It saturates, right? So if the electric field was high enough, I might have to replace mu p times e by the saturation velocity for holes, for example, okay? And that might saturate at a different from the saturation of electrons, right? And that was one of the problems in the midterm exam, all right? So that's the only other caveat. So like I said, study this figure very, very carefully because all device physics is an application of this master equation, okay? Now, what we'll find when you start looking at devices from the next class, we'll start with p-n junctions, is in general, not all 4 components of the current are going to be relevant, okay? Maybe only one is relevant at a certain location, another component might be relevant at another location, and so on and so forth. But this is the most general expression, okay? All right, any questions? So, like I said, that's perhaps the most important equation in this class in terms of device physics, okay? So make sure that you understand every single bit of it very well. All right, next what I'm going to do is I'm going to prove a couple of theorems, all right? The first theorem is in equilibrium, the Fermi level in a semiconductor device is going to be constant. Who remembers what equilibrium means?
Isn't it where donors and acceptors are
I just told you at the beginning of
evened
this
out?
class. No electric field. Somebody else, Elijah says correctly. There's no electric field. Very good. And there's also no concentration gradients. Okay. So there's going to be no net transport of current from one end to the other. Okay. But it does not mean that nothing's happening. Even if I'm in equilibrium, what's going on all the time that it can't stop. It's a dynamic equilibrium, remember? Because it's constantly absorbing this black body photons from the walls of my room, and that's exciting electron hole pairs. And then after a few nanoseconds or picoseconds, those electrons fall back into the empty hole states, re-emit photons to the surrounding walls. There's a constant exchange of this black body photons, and that's what establishes this N sub I, the intrinsic carrier concentration, okay? So whenever I talk about equilibrium in semiconductors, it's not a static equilibrium, like in mechanics where, you could have a ball absolutely stationary on the table, okay? But of course, even in that case, if you think about it from the point of view of atomic physics, even if that macroscopic ball was stationary, the atoms in the ball are not stationary. I mean, they're constantly going to jiggle around. You have these phonon modes in the ball, right? So you'd have to go to absolute zero temperature to slow down the motion of those atoms. But even at absolute zero, does anyone remember, are the atoms going to be absolutely stationary?
Well, they're still going to have 0 point energy, right?
Excellent, very good, excellent. So even at T equal to 0 Kelvin, where you'd expect classically the kinetic energy to be 0, remember half mv squared equals kT, I just showed that. But even then, quantum mechanics tells us you can keep the atoms or electrons stationary, okay? Mr. Heisenberg tells you that you have the 0 point motion. So things are very strange in quantum mechanics. All right, so let's prove that equilibrium Fermi level is constant. Now I'll give you several interpretations of the Fermi level today, okay? The first time we met the concept of the Fermi level, of course, was in the context of the Fermi-Dirac distribution function, where we plotted f of E as a function of E, and you got this sort of a curve, remember? Where at the Fermi level, the average occupancy is half. Below the Fermi level, it asymptotes to 1. It cannot be more than 1 because of which principle? Anybody?
Pauli exclusion principle.
Very good. Above the Fermi level, it dies down exponentially with energy, and that's my classical Maxwell-Boltzmann expression, e to the power minus E over KT, okay? Lower the temperature, the more step-like this function becomes. So the physical interpretation of the Fermi level that I gave you in chapter 3 was, it was the energy level where the average occupancy was half of quantum states, or the highest occupied energy level at T equal to 0, okay? And that gives what's called the Fermi surface or the Fermi sea. Just as a reminder, don't confuse this F of E as the probability of occupancy. It's the average occupancy of a quantum state, okay? But people will sometimes properly call it the probability of occupying quantum states because the values happen to range, the average occupancy for fermions happens to range between 0 and 1, just like probability. Okay, but as long as you're clear in your mind, experts in the field will very often kind of sloppily call it probability of occupancy. That's really the average occupancy, expectation value of the occupancy. Okay. All right. So what I'm going to prove is another physical meaning of the Fermi level. Okay. To do that, we imagine a junction of two different semiconductors. It doesn't have to be a p-n junction. Okay. I have a system 1 and a system 2 that I'm joining together. Okay. And I let it rest so that it reaches equilibrium. Okay. So that there's not going to be a net transport of electrons or holes from one side to the other. Okay. Now you can write down a rate of flow from system 1 to system 2 as the density of states in semiconductor 1, say. It doesn't even have to be semiconductors. One could be a metal, the other could be another metal or another semiconductor. So this is a very general theorem. Okay. So density of states in material 1. Who remembers what density of states is? N1 of E times dE is what?
The number of allowed states between E and E plus DE.
Very good. So if the energy axis pointed upwards and I had some density of states, that tells you the number of available states between E and E plus delta E. Okay. So that's my N of E dE. Okay. I take this Fermi-Dirac distribution function. Now here the energy axis is pointing horizontally. I want the energy axis to line up. So as we did in chapter 3, I take this and turn this figure by 90 degrees, and then I'll get something like this. Okay. So now my F of E is here and energy increases upwards. Okay. So I look at these corresponding energies and I get the corresponding occupancies F of E. Okay. Now for these particles to go to the right, in order to keep Mr. Pauli happy, what should be the occupancy of those corresponding energy levels? Can they be occupied or must they be empty? I'm looking at a particular energy level, E, say.
Can you repeat the question?
So if I'm looking at a particular energy level, okay, and suppose this energy level was occupied in system 1, that occupancy is given by the density of states N1 at E times F1 at E, okay? And I want to find out the rate at which it's going into system 2, okay? So the question is, if I'm looking at a particular energy E, to go from 1 to 2, of course, in system 1, that state has to be occupied, and that's given by density of states value at E times F1 at E. F1 is the Fermi-Dirac distribution function in material 1, okay? And for it to go to system 2, the question is, does this state have to be occupied or empty, or I don't care?
Unoccupied.
Unoccupied. Otherwise, Mr. Pauli would turn over in his grave, right? So therefore, for material 2, I look at the density of states at E in material 2, that's N2 of E, times 1 minus F2 of E, because that has to be empty. Similarly, I can have a reverse flow from 2 to 1. So that's given by N2 of E, F2 of E, because that state has to be occupied by electron. But then this state in material 1 has to be empty. So that's now density of states N1 times 1 minus F1 of E. Okay, so this is a very general principle in thermodynamics or statistical physics. Okay, it doesn't have to be for semiconductors, it's true for any materials. Okay, now at equilibrium, of course, you'd expect these two rates to be equal to each other, right? You'd have statistically the same number of particles going to the right as going to the left. Otherwise, you're not getting an equilibrium. I'm not saying that they're static, they're executing random Brownian motion, but there's no net flow. So I set the two rates equal to each other. I put down the expressions for F1 E and F2 of E, okay? And that's these, okay? And I'll not go through every single algebraic step, okay? You'll find that there'll be a lot of terms that cancel each other, okay? And the punchline would be, you can prove F1 E must be equal to F2 of E, okay? So this expression must be equal to this expression over here, and all energies. So this is a more strict statement. So not only is there no net flux across this boundary between 1 and 2, that's true at every single energy. What does that mean? What I'm saying is you cannot have a scenario where I have a net flow of particles to the right at, say, a higher energy EH, okay? And the same number of particles flowing at a lower energy to the left. That will take care of particle balance, right? So if I had a scenario that I had a higher flow at a higher energy EH to the right, and the same number of particles flowing back at a lower energy EL from 2 to 1, what will be the net current flow across the cross section between 1 and 2? Do you understand the question? I'm looking at particles.
Is that not just what the equation is giving us for the net flow across?
Yeah, it's giving the net flow. So what I'm saying is that this is a thought problem. So I have more particles flowing from system 1 to 2 at higher energies, and that's shown by this dark arrow over here, okay? And the same number of particles flowing to the left, but at a lower energy EL, okay? If that were to happen, what is the net flow of particles across this boundary between 1 and 2?
Just the two arrows added together.
Right, so so what is the value? If the same number, if I have a certain number of particles flowing to the right at a higher energy, and the same number of particles per second.
Smaller number moving to the right overall.
No, maybe I'm not making my question clear. So just think of the number of particles flowing per unit area per second, okay? I have a certain number of particles, say I high, flowing to the right, okay? But at a higher energy, that's a higher energy. And the same number of particles flowing to the left, but at a lower energy. So I low energy. What will be the net flow of particles?
Zero.
Zero. It'll be zero, right? So the net flow of particles is zero. But is this still equilibrium? Now let's turn to the energy term, okay? So what I'm claiming is I have a scenario where I have a certain number of particles flowing to the right at a higher energy, and the same number of particles flowing back, but at a lower energy. In this case, now looking at the energy flow, which way is the net energy flow? Not the particle flow, but the energy flow. Is it to the right or to the left? Or is there no net energy flow?
To the right.
To the right.
To the right. To the right. So what would happen then is the right side would gradually heat up and the left side would gradually cool down. So you're getting a refrigeration for free, and that violates the principle of thermodynamics, okay? So what you have to have is not just a situation where the net flow of particles to the right and the left cancel out, but they cancel out at every single energy. And that's, of course, a more strict restriction, right? And that strict restriction is known as a principle of detailed balance. Okay? So what I'm saying is, when I equate these two expressions by simple algebra, you have to have the same flow of particles either way at every single energy. Okay? And based on that, then you can show that EF1 must be equal to EF2. Let me repeat that. So in equilibrium, obviously there can be no net flow of particles, right, across this boundary. But that's not enough. There has to be no net flow of particles at every single energy. You cannot have a scenario where I have a net flow to the right at a higher energy, say, and the same number of particles flowing back at a lower energy, because in that case, you have particle balance, but you don't have energy balance, right? One side heats up, the other side cools down. So instead, what you have to have is you have the same number of particles going back and forth at every single energy to make sure that the temperatures don't change and there's no net current. Is that clear to everybody?
Yeah, that makes sense.
Yeah. So that's this very important theorem in physics known as principle of detailed balance. So the term detailed balance means you have a balance of flows, not just overall, but at every single energy in the distribution. Okay. And based on that, I'm not doing the exact algebraic steps. You'll see that a lot of the terms cancel out. Okay. N1, N2 cancels out on both sides. Okay. And you end up getting F1 at every energy equal to F2 at every energy. Okay. And from that, you can clearly see that EF1 must be equal to EF2. So in equilibrium, in a semiconductor device, the Fermi level has to be constant everywhere. We'll see in a second that the physical meaning of the Fermi level is it's the analog of water pressure in a system. Okay, I'll elaborate on that in just a second. Okay, now I'll prove another very important theorem in equilibrium. Okay, so in equilibrium, let's look at hole current densities. Okay, I like working the math out in terms of holes because the hole charges are positive and you don't get confused mentally. You know, flow is in one direction, the current's in the other direction. Let's just work with holes. You get the same result in the case of electrons also. Trust me. Okay, so I look at the current density expression that I wrote down. So this is the first term, which is the drift current. Okay, but now I'm looking at a situation which in general is a position dependent current. Okay, so it's JP as a function of X. So electric field could in general be a function of X, may not be a constant electric field, times concentration of holes, times the mobility, times the charge of the holes. Now just looking at this expression, can anyone tell me, is this a low field or the high field expression?
Low field?
Low field, because
Just
I'm
for
assuming,
holes?
exactly, very good. Because I'm assuming that the drift velocity of holes is proportional to the electric field and the proportionality constant is the mobility. If it was a high field value, how would this expression change? It would be Q px times
VSAT.
VSAT, very good, okay? The next term is the diffusion. So that's given by the concentration gradient minus dp dx, okay? P is a function of x. The proportionality constant is the whole diffusion coefficient d sub p, all right? The whole charge is positive, so the minus sign stays put. For electrons, the minus dn dx would have canceled out the minus q and it would have gotten a plus q in the case of the electrons, okay? Now this, of course, in equilibrium must be equal to 0, right? There cannot be any net flow. So you could have, say, a drift current, but you'd have to cancel by an opposing diffusion current at every single energy, all right? And then simple algebra, you can write down an expression for the electric field, okay? Just simple algebra. It's dp dx, you bring the p to the right-hand side, it's 1 over p dp dx. The q's cancel out, I get dp over mu p, the diffusion coefficient over the mobility of the holes, all right? Now from chapter 3, you may recall that I wrote down, I derived an expression for the whole concentration, which is the n sub I e to the power ei minus ef over kt. So this was in chapter 3, hopefully you remember that. We just had the midterms. So let me write down. So ef, that was ei, more or less in the middle of the gap, okay? I suppose it was p-type, so my Fermi level will be in the lower half of the gap, okay? So so we are able to write down the whole, whole concentration, either by referencing it to ei or with respect to EV. So with respect to EV, that was n sub b e to the power minus EV minus EF over KT, okay? Or I could reference it to the EI and I get this expression. Remember that from chapter 3? Okay, so what I do is I substitute this over here and I take the derivative of dp dx, okay? So now remember, this is a function of x. EI can be a function of x. So I'm not having a constant bandage as shown over here. If I had a constant bandage, what is the electric field in this case?
0.
Very good, because electric field, remember, is given by 1 over q, either dEc dx or dEv dx or dEi dx. They're all parallel to each other, okay? So if I have a band diagram like this, my EC, EV, and EI are varying. This is meant to be a straight line. Is this a constant electric field or a varying electric field?
Constant.
Constant electric field. Okay, you'll find, if you do the math, you'll see that the electric field points to the left. It's a negative slope, right? If you had a varying electric field, how would the bands vary? Well, you'd have varying slopes, right? What is my electric field here?
Zero-ish.
Yeah, zero-ish, very good. Electric field increases. At the point of maximum slope, it's highest, electric field decreases, and then it goes zero-ish, like zero-ish. All right. So E as a function of X, E as a function of X in this general case, you simply get 1 over P dP dx, okay? You take the derivative of this, EI is a function of X, simple calculus, use the chain rule, okay? You'll find you end up getting this, okay? Now in equilibrium, I said that the Fermi level is what? I just proved that in the previous theorem. In equilibrium, the Fermi level has to be constant. So if I plot EF, it's going to be flat. So DEF dx will be equal to 0, right? Yeah. So all that I left with is DEI dx. But what is DEI dx correspond to? DEI dx or DEC dx, DEV dx, they're all parallel to each other. EV, EC, EV, and EI are all parallel to each other. 1 over Q DE dx, DEI dx is nothing but the electric field, right? So DEI dx gives you the electric field. 1 over Q DEI dx gives you the electric field, okay? So on the right-hand side, the DEI dx gives you electric field term, which cancels with this. And what I then am left with is this expression, dP over mu P equals KT over Q, KT over Q. Okay, because DEI dx is electric field times Q from this expression over here, right? So the electric field terms cancel out, and then dP over mu P becomes KT over Q. You do the same analysis in terms of electrons, you'll prove dN over mu n is also equal to KT over Q. And this theorem was first proved by a physicist you may have heard of once in a while, Albert Einstein, and it's known as the Einstein relationship. Okay, he proved this. If you read the history of physics, they said that 1905 was a miracle year in physics because in that single year, 26-year-old Albert Einstein proved the existence of atoms based on Brownian motion, and a corollary to that was this Einstein relationship. And then, by the way, he also came up with the special theory of relativity and the photoelectric effect and things like that. Now, if you think about it, that's a very strange relationship, right? Because it tells you the diffusivity, which captures the physics of statistical flow from a high to a low concentration region because of this random Brownian motion, is somehow related to mobility, which is motion not due to concentration gradients, but due to electric fields. Why on earth would mobility, which determines drift current, be related to diffusivity, which is statistical flow in the absence of electric fields, but due to concentration gradients, right? I mean, they seem to be totally different physical phenomena. Why the heck are they connected at all? Well, Einstein realized that they're both ultimately connected by this random Brownian motion that we talked about, okay? So what's going on? Well, we already saw that in the case of diffusion, if I had high concentration, say on the left, then on the right, these are executing random Brownian motion. These are also executing random Brownian motion. But if I have a higher concentration over here, there'll be a net flow to the right. That's my diffusion physics, right? How about for drift? Well, let's assume that I have electric field to the right and assume that these are holes. What's going to happen? Well, this Brownian motion is not going to stop. But now what's going to happen is in the presence of electric fields, this random Brownian motion will go on, but there'll be a net motion of these whole ensemble of holes to the right with an average velocity given by mu p times electric field. So this well-directed velocity, the drift velocity, mu p times electric field, will be superimposed on top of this random Brownian motion. While in the case of diffusion, it's a random Brownian motion which drives a statistical flow from the high to the low concentration region. So it's a random Brownian motion which is common between this diffusion physics and the drift of particles. And these particles could be not just electrons or holes, it could be other types of particles also. It could be, perfume molecules that I talked about, where of course for perfume molecules, the analog of the electric field would be this fan blowing, okay? All right, so now let's try to prove that expression, the Einstein relationship from simple back of the envelope estimates. So the thermal velocity we saw is given by the mean free path, the average distance between collisions, L, divided by the mean free time, the average time between collisions. Also from the equipartition theorem, I just stated without proof that the average energy per degree of freedom, half mv squared, is given by kT over Q, okay? Combining these two expressions, you can write L times V thermal is equal to V thermal squared, okay? And then I multiply and divide by mass because I want to get half mv squared term over here, okay? So mv squared V thermal over 2 will give you kT over 2, okay? Then I also multiply and divide by Q, the charge of the hole, okay? So this gives me kT over Q, and what's left over is Q tau over n star. And if you remember your expression for mobility in chapter 3, that's nothing but the mobility of the particle. We proved, well, we didn't prove, we stated that the mobility of the particle is given by Q times the average time between collisions divided by the effective mass, the conductivity effective mass. That's this expression over here, okay? So that's a proof of the Einstein relationship. Oh, that L times V thermal, we showed at the beginning of the lecture today is the diffusion coefficient, okay? So D over mu is kT over Q. So that's sort of a hand-waving way of proving the Einstein relationship. But this is the more precise way for using these differential equations. Okay. So in exams, I might try to trick you. Sometimes I may give you a problem related to diffusion, but not give you the value of the diffusivity. I might instead give you the value of the mobility. Okay, so you have to use the Einstein relationship to relate mobility to diffusivity, or vice versa. Okay. Any questions? All right. Now, in non-equilibrium, this concept of the Fermi level, which I just proved is constant in equilibrium, in non-equilibrium, Fermi level is no longer going to be constant. Instead, it breaks down into two separate quantities called quasi-Fermi levels. Quasi-Fermi level for holes, which are called F sub p, and a separate quasi-Fermi level for electrons called F sub n. And these are not going to be constant. They can be a function of position in non-equilibrium. I'm going to introduce these concepts of quasi-Fermi levels using this water pressure analogy that I hinted at, okay? So what is this analogy? Well, imagine beaker tubes of water, if you will, okay? So I've got this big fat tube of water filled up to a certain height, like so, okay? And then another tube of water, a skinny tube filled up to a different height, okay? And connected by a pipe and with a shut-off valve, okay? So the left-hand side tube is filled up to this height, the right-hand side tube is filled up to this height, and this valve is shut off. And then I open this valve. Now, which way do you think that the water will flow? To the left or to the right?
Left.
To the left.
Left. Even though the right-hand side is a skinny cylinder, that doesn't matter. What matters in terms of water flow is the water pressure, right? So this is at a higher level, so it's got a higher pressure that drives the flow this way until in equilibrium, the water level has to be the same everywhere, right? So it doesn't matter, the volume of water doesn't matter, it's the water pressure that matters. Well, the Fermi level is the analog of this water pressure in a system. And just as water flows from a high pressure system to a low pressure system, and in equilibrium, the water pressure is the same everywhere, electrons flow from a high Fermi level to a low Fermi level region until in equilibrium, the Fermi level is constant. Holes, on the other hand, flow from a low Fermi level region to a high Fermi level region. Remember, the holes are absence of electrons. All right, next I'm going to change the problem statement a little bit and say that instead of the water level being flat within this tube, suppose the water level was sloping as shown by this curved line over here. Similarly, on the left-hand big fat tube, the water level was curving as shown over here, okay? So there's a sort of a gradient in the water surface, if you will, okay? And they're still connected by this tube that's initially closed, but then I open it at time t equals 0. Now the question is, how do you think that the water surfaces will equilibrate, okay? Do you think they'll kind of flatten out first within the tubes and then slowly flow from the right-hand side to the left-hand side, assuming this is a very tiny, skinny tube? Or do you think the water surfaces would stay sloped like so, and it would flow from the right-hand tube to the left-hand tube? I mean, you should be able to guess the answer from the tone of my question.
I mean, probably the first water level typically evens itself out before.
Right, very good. Assuming, of course, that this is a tiny, skinny tube, so that the water flow is very slow, right? I mean, if this was a big fat tube, then all bets are off, right? But assuming it's a tiny tube, the water flow is very, very slow. So it would flatten out first within the cylinders and then slowly leak from the right-hand side to the left-hand side. That's exactly the right answer. So what I'm saying is you have sort of a local equilibrium within the cylinders first before there's an overall global equilibrium, okay? This local equilibrium within the cylinders is the analog of these quasi-Fermi levels, okay? So now moving from water cylinders to energy bands, see if I have a conduction band, EC, and a valence band, EV, now shown in terms of the band structure, or I could show that in terms of the simplified band diagram. If I create a high energy distribution of electrons in the conduction band and a high energy distribution of holes in the valence band, what will happen is, because of these collisions or scatterings between perfections, this high energy distribution of electrons would first equilibrate within the conduction band, giving you an F sub n, or sometimes we call it EF sub n. That's a quasi-Fermi level, a quasi-equilibrium within the conduction band. And then these holes will equilibrate amongst themselves. That'll give you F sub p. And then slowly over time, these electrons would recombine with the holes, giving off photons. That recombination from the valence conduction to the valence band is the analog of this water going through this skinny tube. Okay, so that's my valence band, say. That's my conduction band. I guess I show it over here. Okay, and the slow leak is this relatively slow recombination rate. So the equilibration within the band is much faster than recombination between the bands. Okay, I mean, everything is fast. Even this recombination is maybe in the time scale of nanoseconds, but the recombination, the equilibration within the bands may be on the time scale of femtoseconds. Okay, so there's fast and super fast. Okay, so the equilibration within the bands, giving you quasi-Fermi levels, is super fast, while the recombination between the bands is much slower than that, even though it's still fast. Okay, it will be faster in the case of. Would it be faster in the? Okay, let me ask you: is this a direct band gap or an indirect band gap, as shown?
Direct band gap?
Direct band gap, yes. On the other hand, if the conduction band was like so, that's indirect band gap, that would be a slower recombination. Okay, that's a faster recombination. All right. Now, these quasi-Fermi levels are applicable in non-equilibrium and refer to local equilibrium within a band. Physicists also call quasi-Fermi levels IMREFs. Anybody guess why? It's Fermi spelled backwards. Okay, so physicists do have a sense of humor, contrary to what you hear. All right, the concept of this quasi-formulas is nice because all that you need to do then is take the expressions that you derived in chapter 3 for equilibrium, and in non-equilibrium, wherever I have the formulable, I replace that the corresponding quasi-formulable, Fn if I'm looking at electrons, or Fp if I'm looking at holes. Okay, and then you can see how these change now as a function of position, and you can get position-dependent phenomena. Okay. So that leads me to the final theorem. So now I write down an expression for, say, the current density to electrons. Okay, you get the same type of expression if I did it for holes. So write down the drift current, Q mu E, but they're all functions of position, plus the diffusion current driven by dN dx. Notice now I'm showing a plus sign because the minus Q of the electron charge cancels with the minus dN dx. Okay, so you end up getting a net plus sign over here. All right. Now I write down the expression for the electrons in non-equilibrium in terms of the quasi-formulable Fn, which in general going to be a function of x. So that'll be, sorry, it'll be some Fn of x in general. Okay. So as we did in the case of the equilibrium case. Oh, by the way, first of all, since this is non-equilibrium, can I set that equal to 0 as in equilibrium?
No.
No, you
so
can't.
you cannot. So you cannot use that expression in the equal to 0 thing as in equilibrium. So it's not equal to 0. Okay. But the rest of the analysis is the same kind of math as before. Okay. So I write down a derivative for dN dx using this expression for n, using the chain rule in calculus. Okay. Plug that in over here. And then you'll still get the di dx, which will cancel with this electric field term as before. Okay. And now you'll find that you'll get a net non-equilibrium current, which will be given by dFn dx. Now in equilibrium, this Fn and Fp in equilibrium would have both given you EF, which is constant. So then dEf dx is equal to 0, we said, right? But in non-equilibrium, that's no longer true. You get a separate Fn of x, Fp of x. It can vary in all different kinds of ways. And then dFnx or dFpx is not going to be equal to 0. And that then gives you the non-equilibrium electron current. Similarly, you have a non-equilibrium hole current. Okay. So this is a compact expression which captures both the drift current and the diffusion current, written in terms of a gradient of the quasi-formula. So starting from next class, when we start looking at devices, we'll sort of plot out these quasi-formulables, and wherever there's a gradient of the quasi-formulable times the local concentration times the mobility will give you the net total current, drift plus diffusion. So it's a very powerful expression. If I was looking at equilibrium, both Fn and Fp merge with EF, which is constant, and therefore dx of EF is equal to 0, and you get an equilibrium current of 0. Okay. So I haven't gone through every single step. Trust me, it's simple calculus chain rule. Okay, so make sure that you can reproduce this expression over here. Okay. Oh, for this, of course, you still, I forgot to mention, you have to use the Einstein relationship because, you know, you have D and mu. So you replace D over mu by KT over Q to get this final expression. Okay. All right. So on Wednesday, we'll prove one final theorem, which is known as the continuity equation, okay, which is a bookkeeping equation. So there, what we'll look at is a non-equilibrium current flow, say for holes, where at a cross section X, I have a current density JP of X, and at X plus dx, I have current flow out of JP evaluated at X plus dx. And I want to see what the time-dependent concentration of holes is at location between X and X plus dx, the small volume, okay? So del P del T, the time rate of change of the hole concentration in this volume would depend on the difference of the current flowing in minus current flowing out, as you might expect. If there's more current flowing in than flowing out, what would you expect would be the hole concentration with time? Would it increase or decrease with time?
Increase.
Increase.
with time, right? On the other hand, if there's more flowing out than flowing in, it will decrease with time. So that's all there is to the continuity equation. So we'll prove that the time rate of change of carrier concentration is the difference of the current flowing in at x minus flowing out at x plus dx, and divided by the volume dx, and then the limit of dx going to 0, that'll give you d minus dp dx. Sorry, it'll give you minus djp dx in 1D. In 3D, it'll be ddx, ddy, ddz. So that gives you the divergence, okay? But then on top of that, you also have to worry about generation recombination. Okay, so if there's generation of carriers, that adds to del P del T. If there's recombination of carriers, that decreases del P del T. So that's my continuity equation. Okay, we'll prove that, and then we'll solve the problem based on that, and that will then set the stage for device analysis. All right. See you on Wednesday.
Thank you.
Thank you.
Thanks.
Have a great day.